Okay, so welcome to this next video in the playlist on Galois theory. In this video, what we're going to talk about is the concept of a field extension. Okay, so we're going to start off with a revision of the definition of a field, and we're then going to look at motivation for the definition of a field extension. Okay, so we're going to go to the polynomial equations and see why the concept of a field extension is intertwined with polynomial equations within a field. And we're then going to look at the rigorous definition of a field extension, and then also a more helpful interpretation, because the rigorous definition and the more helpful interpretation, the cruder interpretation, are slightly different, and we're often in videos, in subsequent videos, we're going to use the cruder interpretation rather than the rigorous definition. It's only very rarely going to be necessary to go back to the fundamental rigorous definition of a field extension. The cruder interpretation is really the soul of what a field extension is, rather than the rigorous definition. Okay, so we'll start off with the definition of a field, because fundamentally field extensions are ways of making fields bigger. Okay, so what is a field? Okay, so a field is an algebraic structure, basically. It's a set, and they're usually denoted by an F. Okay, so a field is fundamentally a set of symbols. Okay, so you have some set containing a bunch of symbols, and on this set of symbols you have defined two operations. So you have an addition operation, and you have every symbol in both of these here. So you'll have every symbol in the column here and every symbol written out in the row here, and then you have defined what any symbol, let's say A, plus any other symbol B in the field is, basically, and you have given the answer to that here. Okay, then you've also defined a multiplication law on this field, and again we can draw up the Cayley table for this. You have every single element of the field written in this column, and also every single element of the field written in this row, and you have defined what every element, let's say A, in the field multiplied by any other element B, which is also in the field, is, basically. Right, now in order to be a field, these two operations have to obey certain properties. So firstly, the addition operation here has to be a abelian group structure. Okay, so let's just remind ourselves of what the definition of an abelian group is. So an abelian group is a group which is also commutative. So what are the axioms of a group, firstly, then? So the first axiom is that you have to have an identity element. So there is some element within the set such that when you add it to any other element of the set, either on the left or the right, so if you take, we often call the additive identity 0. Okay, so if you take the additive identity and add it to any element where this element is on the this element here is on the right here, you take 0 and you add it to every possible element in the field, then that is going to just give that element of the field back again. So for any B, it will just give B, basically. And also, if you take it on the other side, where the unspecified element is on the left, and you add it to the identity, so this time we've got any element here, and we're adding it to the additive identity, and that will again just give this element back again. So it specifies instantly what this first column here of the Cayley table and what this first row of the Cayley table must be. Okay, it basically tells you that this first row is just this row up here translocated down, and this first column here is just this column here translocated along, basically. Okay, so there is some additive identity. Secondly, it must obey the associative property. Okay, which means that if you take any element A and compose it with an element B, okay, that will give you some answer. Take this element and then compose it with a third element, C, this must be the same as if you take the element A and you compose it with the answer to B plus C, and that is not trivial, not in the slightest, because A plus B is some new answer. It's this answer here, basically, in the Cayley table. Okay, and you take this new answer and then compose it with C. Also, B plus C is some new answer in the Cayley table, and you take that new answer, which you don't have control over, and you take A on the left and compose it under addition with that answer. Okay, so it's not trivial that that's true at all, basically. Okay, thirdly, you need inverses. So for all elements in the group, okay, there must exist another element. So for all, for all A is an element of this set F, there must exist another element, A inverse. It's not often denoted A inverse like that. Instead, it's often you put a negative in front, since we're talking about the addition operation, such that if you compose A under addition with its additive inverse, you'll get the additive identity back again. So there should be inverses under addition. And then finally, because it's an abelian group, it should be commutative, basically. Okay, which means basically that the Cayley table is symmetric down the diagonal line. Okay, it means that if you take A and add it to B, okay, the answer there is the same as if you take B on this side and add it to A, okay, B plus A down here, okay. And again, that's not trivial. That's saying that the entries in the Cayley table that are the reflection of one another down the diagonal line here. So if you take the reflection of this entry here, it's in the diagonal line, it's this entry here. It's saying that those two are going to be the same, basically. And again, that's not trivial. For groups, it doesn't necessarily hold true that that has to be true. Okay, right. So that's the structure that we have on the addition property. Now on the multiplication property, we insist that it is almost a group. Now, you can't insist that it is a group itself and also have the distributive property that's going to connect these two, okay? Because the instant you insist on the distributive property, you are given something which prevents you from having multiplicative inverses for every element. So the instant you assume distributivity, okay, of multiplication over addition, then the answer to 0 times anything, okay, so if you take 0 times any other element of the field, that always equals 0. So the 0 is the symbol, remember, for the additive identity. So if you take the additive identity and multiply it by anything, because we're later going to insist on distributivity, this forces all of these answers to be 0, basically. And that doesn't allow there to be an inverse for 0, because 0 sends every other element to one element of the field. It sends it to 0, basically. And you can't invert that mapping, basically. It doesn't have an inverse. Similarly, if you multiply on the right by 0, that also sends everything to 0, which tells you that this column here is also made up of entirely zeros. Okay, so that means that you can't invert 0, so you can't have an inverse for 0, but you try your best to make this a group. Okay, so firstly you're going to insist on, and I should probably maybe make this property 5, but I'll call it property 1 again. Firstly you insist on there being a multiplicative identity. And this is not obviously going to be the same as the additive identity, unless you're talking about a field that consists of only one symbol. But if you have a field that consists of more than one symbol, it clearly can't be the additive identity, because the additive identity sends everything to 0 and not to itself. But there is a multiplicative identity, which is a symbol that usually is called a 1, basically. And if you take 1 and compose it under multiplication with any element on the right here, it will map that element onto the same, it will map it onto itself. And similarly, if you compose it with any unspecified element that's on the left, that will also map you onto that unspecified element. So there is a multiplicative identity Okay, second, we also insist on multiplicative associativity. Algebra really is the study of the associative property. The associative property is what makes algebra interesting, basically. Okay, so the associative property tells you that if you compose A and B together via multiplication and then compose the answer to that with another element of the field via multiplication, that this is the same as if you take A and then multiply it by the answer to B composed with C, basically. Okay, and again, that is not a trivial property. And then thirdly, you then insist on there being inverses for all elements that are not 0, basically. Inverses for all non-zero elements, except for 0. So you want a multiplicative inverse to everything except 0. Okay? So, basically, if you take any element A, there should be another element which is A inverse, such that if you multiply A by A inverse, you'll get the answer 1. Okay, so there's no element A inverse for 0, but for every other element there should be an inverse. Okay, then finally, well actually not finally, but also you're going to want commutativity, okay, which again means that the Cayley table is going to be symmetrical down the diagonal. A multiplied by B should equal the same thing as B multiplied by A. So if you take A and multiply it by B, you get this answer up here. If you take B and, whoops, have I smudged that? Yes. If you take B and multiply it by A, you'll get this answer down here. And you want those to be the same. Those entries need to be the same. So entries that are opposite one another, or reflections of one another in the diagonal line, should be the same, basically, is what commutativity tells you. Okay, and then finally you have the property which links addition with multiplication, and this is the property which forces 0, the additive identity, multiplied by anything to equal the additive identity again. This is the distributive property, so this is the main one that connects the two. Because of course, why can't you just define this to be a group? Well, you could. You could insist that you could just define two groups sitting on top of one another on the same set of symbols, but it won't be very interesting. You want the two to intertwine in some incredible way. You want them to interplay. And the distributive property is this interplay between addition and multiplication. It tells you that if you take A and multiply it by the answer to B plus C, that's the same as if you take A and multiply it by B, get that answer and add it to A multiplied by C, and that truly is not trivial. Okay, so if you compose B and C together under addition, that will give you some answer. Take that answer, take A multiplied by that answer, you'll get some final answer. Okay, and I'm saying that that's the same as if you take A, multiply it by B, take A, multiply it by C, you'll get two answers here, and then add those two together. That's not trivial at all that is true. Okay, but this is the interplay that you have between multiplication and addition, and the instant you insist on that being true, and I should also add that what I've written here is what's known as left distributivity, because the A is multiplied on the left of this. Now there's also right distributivity where the A is multiplied on the right, okay, but because of commutativity, if we've got left distributivity, we also have right distributivity. Okay, so this is left distributivity. Right. Okay, so why does this instantly mean that the additive identity has to multiply by anything to give the additive identity? Well, it's because if you take A and you have it multiplied, let's say by any old number you like, B, okay, then what we can say is that B is the same thing as B composed by addition with 0, because 0 is the additive identity. So if you compose B under addition with the additive identity, you're going to get back B. Okay, so we can substitute that in here. So A times B is therefore equal to A times B plus 0. Okay, but then we can apply left distributivity here, and we get that this is A times B plus A times 0 Okay, so now look at this. We've got a times b is equal to a times b plus a times 0. But a times b is just some symbol within the set, basically. So we can now say, okay, it must, whatever that symbol is, it must have an additive inverse. So we'll compose on both sides with the additive inverse of a times b. We'll then use associativity on this side. So let me show you. So we'll compose with the additive inverse of a plus b. Okay, like so. So we've composed on this side with the additive inverse of a plus b. Now we'll compose on this side, so negative a times b, and then it's added to, and then we've got a times b plus a times 0. We'll then apply the associative property to associate this one with this one. Okay, so we'll get that the additive inverse of a times b composed under addition with a times b, and then composed under with a times 0. Now, we can compose these two together and get that that's the additive inverse. We can compose these two on this side to say that that is the additive inverse. We get that the additive inverse is the additive inverse plus whatever this number is. But of course, the additive inverse plus anything is just itself. So this is a times 0. So that tells us that anything times 0 is just the additive the additive identity. Okay, right. And you can do a similar argument where you show that the additive identity multiplied by anything the other way round, so 0 times a is also 0, but of course you can get that from commutativity as well, but all you do is use right distributivity rather than left distributivity. Okay, so as soon as you insist on distributivity, you get that all of any number multiplied by the additive, the additive identity must give the additive identity. Okay, right, so that's a revision of the definition of a field. Now let's have a look at the motivation for a field extension. Okay, so let's look at the archetypal example of a field. Okay, and the archetypal example of a field is the set of rationals. Okay, so the set of rationals forms a field under addition and multiplication. So this is the field algebra that most people actually know. It's the one that you learn in primary school. Okay, so let's now look at a polynomial equation within this field. So let's say we've got an equation here, okay, and we've got x squared minus 2x minus 1 is equal to 0. Okay, so this says find me a number such that if I multiply it by itself and then subtract off, which means add the additive inverse of 2 times that number, and then also add it to the additive inverse of 1, then the answer needs to be equal to 0. Find me a number within this set of symbols such that this is true, basically. Okay, right. So there is a very handy trick here, which is completing the square. Okay, so we can say, if we look at x minus 1 squared, then if we expand that, we get x, well actually let's just write it out in full. This means x minus 1 times x minus 1, but we can then use the distributive property to say that this is x times x, which is x squared, minus x from this one, minus another x from here, and then add that to 1, which will give us x squared minus 2x plus 1. Okay, so if we then subtracted off 2 from both sides, this would actually equal this. So basically, x minus 1 squared minus 2 is equal to 0. This is basically exactly the same as this. If you take any number x within the rational numbers and work out this, it will be the exact same as if you take that number x and put it into this, basically. Okay, right, so now this is helpful because it allows us to assess whether there are solutions to this equation, because if there was a solution to this equation, it would have to satisfy this equation, obviously. Okay, so it would also therefore have to satisfy this equation. So I can take the 2 to the other side. So if it satisfies this equation, then it will also have to satisfy this equation, because all I have literally done is added 2 onto both sides, basically. Okay, so if any number which satisfies that will also satisfy that, and any number which satisfies this will also satisfy that. Okay, so if there was some x which is an element of the rational numbers, then if you take 1 from that x, so if you subtract off 1, if you add the additive inverse of 1, but often I'll just say subtract rather than say add the additive inverse of 1. If you subtract off 1 from any rational number, that's still going to be a rational number. So taking off 1 does not change the fact that you are a rational number. Okay, so if you subtract off 1, you'll still be a rational number. So x minus 1 is a rational number. So this number in here, which we are squaring to get 2, would have to be a rational number. Now, there is no rational number that squares to give 2. So there can be no rational number x which satisfies this equation. Okay, so I think we should just quickly prove that there is no rational number that squares to give 2. Okay, so if there was a rational number that squared to give 2, let's just try and prove this. So let's suppose that there was some rational number which we'll just call x, which squared to give 2. Then basically x could be written as an integer over another integer. So a and b are both integers. Now, let's assume that we cancel this down as much as possible. And what do I mean by that? Well, basically we know that rationals are kind of degenerate, okay? So fractions are degenerate. There is degeneracy in the set of fractions. So for instance, a half is the same as 2 quarters, which is the same as 6 over 12, which is the same as, let's go for another one, 24 over 48. So there are loads of fractions which are all the equivalent number. So basically I want you to cancel down as much as you possibly can. So I want there to be no common factors between these. I want there to be no further cancellations that you can make. So I want these two numbers that you've put here to be as close to 0 as you possibly can make them, basically. Okay, so I want I want there to be no common factors between A and B. Okay, so I want it, you'd pick a half if you were to pick one of these to represent the fraction. You wouldn't pick any of these bigger ones. I don't want there to be any cancellation that you can make. Okay, right. Then, A over B would have to square to give 2. Okay, but we can multiply this out and we get that this is A squared over B squared, and this must equal 2. Which implies that A squared would equal 2B squared. Now, this is going to lead to a problem, because that means that A squared is even if it's 2 times B squared. B squared is some positive integer, because B was an integer, so you've squared it, and therefore you've got some positive integer. And when you multiply any positive integer by 2, you're going to get another positive even integer. Okay, now let's just have a look at some examples of squaring numbers. So if we look at some integers here, and let's square them. So if you square 1, you get 1. If you square 2, you get 4. If you square 3, you get 9. If you square 4, you get 16. If you square 5, you get 25. If you square 6, you get 36. Which square numbers are even? Well, 4 is even, 16 is even, 36 is even. Okay, and these are all square numbers which came from squaring another even number. Whenever you square an odd number, you get another odd number. Okay, so if we are squaring a number and getting an even number, then that must have meant that the original number we squared was also even. Now, okay, I've given you a bit of empirical evidence here, but that's not a proof that if you square a number and get an even number, it must be because you've squared an even number. So let's just prove that. Okay, so if you take an even number, okay, such as, let's say 2n, okay, so that's definitely an even number, and let's say n is just some integer, and you square it, then that will give you 4n squared. So that's also going to be an even number, because if n was an integer, let's say a positive integer, then when you square it, you'll still get a positive integer, and it's multiplied by 4, so it's certainly an even positive integer when you look at 4n squared. Whereas, let's now say we take an odd number. So let's say n again is some positive integer, you multiply it by 2, that will give you some even number, and you then add 1 to it, that will give you an odd number. All odd numbers can be expressed like this. For instance, n is equal to 0 will give you the odd number 1. I know n isn't a positive integer, but we'll make that exception for 0. Okay, n is equal to 3, if we wanted this number to be 3, we'd set n is equal to 1. If we wanted 5, we'd set n is equal to 2, etc. Okay, so if we square this, then what will we get? Well, let's expand this. We'll get 4n squared plus 4n plus 1. Now, 4n squared is again going to be an even number. 4n is an even number, okay, because remember, n was some positive integer or 0. And therefore n squared is a positive integer or 0 again. So when you multiply it by 4, you're going to end up with an even number. And when you add two even numbers together, that will still be an even number. And then when you add 1 to this even number, you'll end up with an odd number. So basically, whenever you square an odd number, it ends up odd. When you ever you square an even number, it ends up even. So if we've got some number which is squared to give an even number, then it's going to have to be an even number itself. Okay, so this now is an even number. So we could express a as basically 2 times some other number. If it's an even number, we can divide it basically. So let's divide it by 2, and then that answer of a divided by 2 is n. So we can write a as being equal to 2n. Now substitute that in. We get that 2n squared therefore must equal 2b squared. Okay, and then multiply this out, and we'll get that this is 4n squared, and it's equal to 2b squared. Cancel the 2's, and we get that b squared is equal to 2n squared, which implies that since n was some integer, okay, it might not necessarily have been a positive integer, but it was some integer, then n squared is a positive integer, and you've got it multiplied by 2, so this is an even number. So again, b squared is an even number, which implies then again that b must have been an even number, because only even numbers can square to give another even number, and therefore b must equal an even number as well. Maybe we could write it as some 2m, where again m is an element of the integers. Okay, but that's a contradiction, because I said cancel this fraction down as much as you can so that there are no common factors, and now I'm saying that I can show you that there are that both of these numbers, both a and b, are divisible by 2. They're both even, so that contradicts me having picked the smallest fraction, the smallest degenerate representative of this possible, basically. Okay, so that's the proof that there can be no fraction which squares to give 2, because as I've shown, it would contradict, basically, it leads to a blatant contradiction. Okay, because if you assume you pick the most obvious representative of the equivalence class of fractions to use, then you can show that you haven't picked that representative, basically, even though you assumed that you had. Okay, so when you get a contradiction like that, it shows you that one of the assumptions you made must have been false. Now, the assumption that we can pick this representative is not false in the fractions. So the assumption that there was a representative, well, there was a rational altogether that squared to give 2 must have been the incorrect assumption. Okay, so there is no fraction, there is no rational number which squares to give 2. Okay, so we'll continue this discussion in the next video.